Hi everyone. In this video, I'll be training a ResNet model on CIFAR-10 dataset for classification task, and I'll be using PyTorch machine learning library for the implementation. So the idea is to implement and discuss the most commonly used functions and my preferred way of using them to create this pipeline. So let me first import the torch package. And then because CIFAR-10 is an image dataset, I also want to import the torch vision package. Maybe I can also show the package here. So this package has many of the commonly used publicly available datasets, the IO functions, and then these torch vision transforms, which we would also definitely use. So I'll also import them. Great. Now for the dataset, I can get it from torchvision.datasets.CIFAR-10. I should provide it the data to download the data into, and also download it only if it's not already downloaded. And at this point, I can specify the transforms that I would like to be applied on the data while it is being loaded into memory. So I'll say transform. And here I can specify. So transforms.compose allows me to specify a list of transforms that I want to be applied on the data in sequential order. So first of all, I definitely want to convert the PIL images in this torch vision dataset to a torch.tensor. So one of the reasons why we use these machine learning libraries like TensorFlow or PyTorch is that we want to take advantage of this multidimensional arrays or tensors in them. These libraries have highly optimized operations that then you can perform on these tensors in both CPU or GPU. And these tensors keep track of all the operations that are being performed on them, and then analytically compute the gradient of the output of these tensors with respect to the inputs to them. And this is very useful when at the end you're training the model, then you want to backpropagate. So here I want the PIL images to be converted into tensors, and this step is going to convert the images to a channel, into height, into width of the images format. And then you also mostly always want to do a channel-wise data normalization, because you do not want, in case your dataset is skewed in one particular channel, you don't want that skewness in the dataset to affect the network training too much. So I can normalize the dataset here. So for that, I should provide this to some statistics on the dataset. And I also want to do this normalization in place, so I can save a copy of the data from being made and save some device memory. So if you're using your own dataset, obviously here the data statistics would be different. So these three numbers are the means for the three channels of my dataset, and these three are the standard deviations of those three channels. You can also compute these for all the images of your dataset and then use those numbers after iterating through your dataset as you put in here. And you can also find them for most of the publicly available datasets online. And for CIFAR-10, we can just safely use these numbers. So now my dataset is going to be in the range of -1 to 1. The operation normalization is doing is this. With these means and these standard deviations for each of the three channels. Now at this point, you may also want to apply augmentations as you're loading the images. So you can specify them also. You can make random crops of the dataset images. The images are 32 by 32, so I want to retain the same size as I make crops. Therefore, I'll also do the padding. I can also do random horizontal flips. So augmentation is generally very useful when you're training models, as they help the model generalize better. So these transforms, they introduce variations in the dataset that you're training on. But you should also be careful that you don't apply augmentations which are so bizarre that after that augmentation is applied, it should not make sense for the network to classify that augmented image as its original class again. So it's good to have augmentations to ensure better generalization for the network, but it should be applied sensibly. So now I can add the train transform here. And now to download the test dataset, I just have to specify here train equal to false. And also, I do not want to do the augmentations for my test dataset. So I can just convert them to tensor and do the normalization for my test images. Oops. There you go. Sorry. Great. So after we've loaded the datasets, I also want to be able to access this data in the dataset in batches, and also probably shuffle them as I load them for training. So for that, I'll use data loader. So that's available in .torch utils package. So I can say I should specify the batch size. And also batch size is one of the most important hyperparameters when you are training the network. Usually you keep it around 32, 64, 128 or 256, something like that. So you could actually probably train on the entire dataset during one iteration for the training. But you would probably not be able to do that because you won't be able to load the entire dataset into the memory if it's too much data in, or if the dataset is very high dimensional as in images. So that is one reason why you have a batch size, which is a smaller subset of the entire dataset. And the other is it's seen that smaller batch sizes help in faster convergence of the model to a good enough local minimum. That probably makes sense because with smaller batch sizes, you can already start making the model learn while it's still not seeing the entire data in the dataset. So you can start optimizing the parameters after it has just seen the first batch. And also it's often attributed that smaller batch sizes introduce noise in the data that is seen by the network in every iteration, and therefore it helps in training the models to have better generalization properties because they're not seeing the entire dataset and trying to learn the conclusion from the entire data, but they're seeing smaller subsets of the data in different orders, and therefore there's some noise introduced in the training process that helps them in converging A, faster, and B, probably not the global minimum, but a good enough local minimum. So here I can specify the batch size and whether I want to shuffle. Yes, I want to shuffle the training dataset. And also one thing I'll do is I'll do pin memory here. And also open the package here, the function here, so we can see what parameters it takes. Is it here? Yeah. Okay, so we specified the batch size, shuffle. So here you can see that you can also provide a sampler here. So what the sampler thing does is that if, for example, you're training the network where you have a strategy on how you want to feed it the data. So you want to feed it the data of the easier examples or the easy to classify images first and then the harder examples, or you have a very imbalanced data set and you want to manually make it more balanced when you're making the batches for the training. So in that cases, you can use a sampler where you specify the indices of the samples in the dataset, and they are iterated over in that particular order. Here it is not required, although let me use random split to actually convert this dataset into training dataset and a validation dataset. Okay. And here you also do the spin memory thing. So what the spin memory thing does is that it allows a faster copy of the tensors from the host memory to the device memory. So if you want to train the model on GPU, then you also have to copy all the data to the GPU memory, and then if you've pinned the memory while loading the dataset into the host, then it will be faster to transfer that memory to the device memory. And actually there's a very nice series of blog posts by NVIDIA. Yeah. Where they explain why pin memory helps. Yeah, here. So it basically copies the memory from the pageable the dataset items from pageable memory to pin memory, and then it is transferred to the DRAM. And therefore, when you specify pin memory to true, you are saving on this operation, and the transfers they mention here about 2 times faster. Okay, and the same thing I can do for the test data loader. One thing you often also want to do is divide the dataset into non-overlapping training dataset and validation dataset. And that you can do using random split from torch.utils. You could also do that with this sampler. So you have the whole dataset, and you could divide the indices of those dataset into non-overlapping regions, say 20% of the dataset indices into validation dataset and 80% into training dataset, and then give those sample indices when you're making different data loaders for the training and validation one. But if you don't have such a preference for which indices you send where, and you don't have a particular requirement for using sampler, then you can just use random split. So here, let me say train indices and val indices, and then a random split of the dataset and let me say validation ratio into length of dataset and 1 minus val. Yeah, right. So then this becomes train dataset, and this becomes validation dataset. Oh. Okay, so these should be integers because this is the number of dataset elements to put in this dataset and the number of dataset elements to put in the other. Great. Okay, so we've loaded the dataset into memory, and we can now access it batch by batch. Maybe I don't want to shuffle the data for the test dataset. This is all good. Okay. So now we can quickly have a preview of the dataset. So preview, just to see how the images look like. So I can take a data loader and I can iterate for the images and labels through it. probably need matplotlib. So plt dot and I can show the images on this plot. Now there's a useful function from Torch Vision utils, which is make grid, that would make a very nice grid of a certain number of images of, using this function. So I'll say show batch, and then from Torch Vision utils, I'll import make grid. Make grid images. How many of them I want in a row, so I can specify 10. And also, if you remember here, when we applied this transform, the images were converted to a channel by height by width format, and when you're showing it using IAMShow, this expects the images to be in this format. So I'll have to do a permute here to ensure that the height is at the first axis, the width is at the second, and the color or the channel is actually at the third axis. Okay. So now I can show the batch for, say, the train loader. Or train. Wait. Not right. Oh, sorry. Aha. It's doing it for all the batches now, so I should stop it. Great. So here I can see a few of the images here. And you see that they appear very dark. And the reason they appear this dark is because we had applied this normalization, which had mapped the data to this range. Now, if you want to actually see them well, maybe you can denormalize the images. We can take an images batch, and we can take the means and the standard diffs. Maybe also let me make the data 64. And do the inverse of what was done there. That is yeah, do this. So I can do return images into LCD devs plus means. So these means and standard deviations, these are actually just 3x1 arrays, and here I'm being able to multiply and add them to the images, which is a batch size into HWC shaped tensor, because of broadcasting. And you can also read about the broadcasting semantics, and here it specifies what are the rules that should be followed so that you're able to do operations on two tensors and have one broadcasted to the dimensions of the other. So in this case, either the number of the dimensions of x and y, they should be equal, in which case you don't need the broadcasting, or you prepend 1 to the dimensions of the tensor with fewer dimensions. So here it's just 3, 1. So I can change the tensor dimensions by reshaping them. So 1 for the height and width. I have 3, 1 for each channel, and I also should have 1 for the batch dimension. Similarly for the standard deviations. Great. And now here I can actually just do denormalization of the images with the data statistics I had specified earlier. And you can see that you find the images as they should appear. Okay, so now we can start with the training process. The first thing that you would want to do is you want to decide what device to run the training on. If you have a GPU, you obviously want to run the training on the GPU. So let's first see what device we have. So for that, I'll specify this function. To check if you have CUDA compatible GPU, you can run this torch device CUDA, torch CUDA.is available, and if this is available, then you return torch device CUDA, else you can return torch device CPU. Okay. And I also want a function where I just give it one tensor or my model or a series of tensors, and it just transfers them to a given device. So I can make this function toDevice. I should tell it the device on where it should transfer and the entity that it should transfer. Now, if that entity is a list of other entities, then I want it to iterate over that list and transfer every entity. So I'll do that. We call the function again, but this time the lm or lm entity, and otherwise just toDevice. Sorry, if it's not a list, then just entity toDevice, and I want to do it in a non-blocking fashion. So non-blocking here means that you do not want the execution of this code on the host device to be blocked until the transfer has been completed from the host memory to the device memory of this entity. So you don't want to block the execution of code on the host memory unless what you're implementing next requires this data to be already on the GPU memory, in which case it doesn't make a difference whether you do non-blocking or not. But if there is some time and there are some other instructions that you can run on the host side, then you can continue running them in a non-blocking fashion if you specify non-blocking like this, while the data transfer from the host memory to the device memory is taking place concurrently. Great. And here I should also give device. I think this should work. Okay. Now, I also don't want to do this toDevice manually for every image and label batch that I load from the data loader. I mean, I can do that. I can load them from the data loader and then say, okay, images equal to toDevice images and my default device. But I also want it to happen automatically when I'm iterating through the batch of the data loader. So for that, I can define a class which is device data loader. And what it should do is that it should basically be a wrapper around my data loaders and transfer the batches to the specified device. So I'll quickly implement this class. I need to tell it the data loader and I need to tell it the device. And device. And so for data loaders, you actually get data from them using this, either the getItem function or the iter function. So here I'm specializing the iter function to automatically first transfer the data loader item to the specified device and then return needs iterator. Self.dl. What? This is what So now I can use an instance of this class the same way I was using the imported data loader from torch.utils.data. I can already say I can get the device here first. Perfect. And now comes the part where we want to train the network, and we want to first specify the architecture of the network. Network architecture. So when you're using image datasets, you mostly use a convolutional neural network. Because convolutional neural networks help in retaining the spatial structure in the images, because there's a correspondence that when you're running convolutions with the kernel over the images, you know that at any point through the depth of the network, the top left part of the tensor output is roughly due to the features in the image which were in the top left region, and then the top right part of my activation map is due to the features which were present in the top right of the image that was fed to the network. And then within this convolutional neural network, you can add and create different types of modules. So for example, you can have a residual block in the neural network, as in ResNet. You can have, maybe I can write it down also. You can have inception module as in inception nets. You can have these depth-wise convolutions, or these inverted residual modules as in mobile net. So you can have all these different modules that you're creating within these convolutional neural networks. Now in this video, I don't care if the network architecture that we're using is the most optimal for this task and this data set or not. Let's just make any network and see how we can create that network and train it. So I'll make a simple ResNet. Actually, you can also make feature pyramid networks and whatnot, but that's probably for another week. Okay. Now what I want is an interface like this, that I should have a model equal to ResNet X, and I should be able to tell it what are the input channels of my data and how many classes do I want to classify them into. And then I should be able to call this model on a batch of images and get outputs like this. So this is the idea. Okay. Now in PyTorch, when you want to create a model, you mostly always want to use this NN module. So it's a base class for all neural network modules, and your model should also be a subclass of this class. So here, there's a very simple and nice example. You have your own model, which is inheriting from this NN module, and you have two layers, convolution 1, convolution 2. You had one input channel, and you were classifying into 5 classes. So here you specified all the layers in your model, and in the forward function, what you do is when you're taking the input, you pass this input through these layers in a sequential order. First through convolution, then through the activation function, then this output back to the second convolution, and then through the ReLU, and then the output. So this is one way to do that. You can also use NN sequential. So when you have a series of such layers. And all you want to do in the forward function is to be able to pass the input sequentially in this, like in the same order as you're specifying the layers here. You just want to pass the input through these layers. Then you can use NN sequential and specify these layers in the input to this. The forward function will automatically pass the input through these in a sequential order. So with this, let me make my ResNet X model inheriting from NN module. Wow. Maybe I should also show what a residual block is while I want to make it. So this is what a residual block looks like. So you have the input coming to these weight layers, which are usually just another convolution layer, and then the activation function, another convolution layer. And at the end here, you would have a number of these blocks chained together. So maybe another block just right here. But at the end, when you have taken the output of this weight layer and ReLU, you add back the input that you gave to these two layers here into the output of these two layers. And why that is useful is that this addition of the input back to the output of this module now reduces the work of this module to not find a mapping from this X to whatever output was to be found here, but now this module only has to learn the mapping between this X and the intended output here minus this X. So earlier, if you did not do this addition here, then the mapping was, say, HX equal to FX. But now that mapping has turned into HX equal to FX plus X, so this FX is now just the difference of what the mapping should ideally learn from X minus X. And the ResNet networks are usually much sparser networks, and they're able to learn a lot more with much lesser number of parameters. So we are going to make a module like this. Keep it like this. And here, make a function which is say residual in block. Okay. I want the number of input channels, out channels. Maybe if you want to do a pooling or not. And in this, I want to create these two layers, and then I'll club these blocks together to form one residual network. And at the end, in the forward function, I can do this addition here to make a complete functional residual block. So this is just one block that's going to go within this residual block. So here, I want the convolution block, in channels, out channels. We'll keep equal to 3 and padding equal to 1. Then I also want to do patch norm 2D, and all these functions actually you get from torch NN. So batch normalization is a very useful regularization technique when training neural networks. What this does is similar to what we did to our dataset when we loaded it. So here we are doing a channel-wise data normalization to ensure that if a channel is very skewed to one particular value, that does not affect the network too much. What can happen is while you're training, your network may get trained such that the output of certain tensors is so large that that then keeps affecting all the rest of the activations and all the rest of the layers following it. So with batch normalization, at every layer you normalize the outputs of all the tensors of the previous layer, and you ensure that a skewness developed within the layers of the network are not propagated. So you do it for all the channels that you're going to output from that particular layer. And then I want to do a ReLU here. Let me do it in place. I think this is all. If I'm pooling, then I can add mn dot max pool 2d with kernel size 2. And I'm returning an sequential object. Great. So now, so this is just a convolution block, right? So it's useful to create this block like this. Maybe I can just say a convolution block, because then it's easier for me later to just club these blocks and also make residual block out of it. So I'll say conv block in channels, because here also I need to know the in channels and classes. Sorry, forgot this. But, and this is going to be very random for now, but let's make one more. And this time I'll have 64 input channels, because 64 were the output channels from this layer. So the next layer is going to get these 64 channels. Let me make it 128. And here I can do a pooling. And then I can do a ResNet block here. And I can say sequential So here I'm keeping the number of filters the same in both the convolution layers and in the previous layer, because then it is easier for me to add this X back into the output of this residual layer. But that's not necessary. You can also keep a different number of filters in these convolution blocks in the residual network, and then you can use 1x1 convolutions to increase or decrease the number of filters so that you can add back the input to the output of these this residual block. Maybe I can just copy paste this. 3, 4, 2. So this should be 128 now. Maybe I can also pool here. And again, making the number of filters the same as the previous layer to ease the addition. So now this part of the network has created a pool of features for us. And now, because I want to do the classification task, I can add a classification head here, which will use these extracted features to classify these images into one of the n number of classes. So I can make a search.classifier here. Then I should flatten the whole thing. I can also introduce a little bit of dropout. Dropout is again a good method to ensure good generalization properties for your network. And then here, so I had flattened out the features that I got from the last convolution layer, and they are 512 in number, and I would have a linear layer into neurons, which are the same number as the number of classes I want to classify into. And now I can also do the forward function here. I'll get the input. And basically I'll pass it through all of these. Just, yeah, do this. This is out. Should do it. And the reason I did not make this NNN sequential in the first place, and I'm defining a special forward function, is because I have to here do this addition explicitly, and that is easier to do. Also, when you're making more complex network architectures, it's easier to do it when you just specify all the layers here, and then you can make links between the different layers as I make it here now. So this. Okay, now all straightforward. And I have res2 out plus out, and then I can return the search dot classifier. Great, so this is our model. Oops, I don't know why I did this. Great. Let's see if we can do this now. Maybe just 3 and 10. Perfect. And you can also print the structure of the model here. So it's this convolution, convolution, residual, convolution, convolution, residual, and then the classification hit. Great. So you can see here, if you wanted, you could also specify the NN sequential thing as an ordered dict. Maybe I can do it quickly. I need some collections. And you can give it a name, conv res1. And okay, and there's one more here. Good. So you could also do it like this, and then instead of this 0, 1, you could actually get the name that you're giving as the key in the ordered dict when you see your model output. So that can be useful sometimes if you have a very complicated model and you have a lot of layers. So then you can use the NN sequential with an ordered dict like this. Okay, so our model is prepared. You can also see the model parameters for your model with this. Oh, and you can not just for the entire model. If you want, you can also see it for a particular layer in your model, for example, say for this. Maybe I can do it for conv1 and here just show this shape so it's clearer. So what I mean to say is you can also access the parameters of not just the entire model at once, but also the different layers or blocks within the model. So here you just get it for the conv1 block in the model. Also for S1. Now we can start training the network. So for this, what I want to do is I want to have something like results, and I want to train. I want to train the model. So first the model. I want to give it the data loader. So my train DL, my validation DL, and then I want to give it a series of hyperparameters. How many number of just epochs do I want to train for? Let's keep it short, 10. Then what is the learning rate? So when I'm optimizing the parameters of the network, I make steps towards the decrease of the gradient of the loss with respect to the network parameters, and learning rate decides how much of a step I make. -2, but I'm going to be using a scheduler and also doing weight decay. Actually, it should be max LR to have a max LR of 1e -2. Then what is loss function I'm going to be using? So when I pass input through the network to get an output, I also have my desired outputs or the desired labels. I want to be able to find how far is my current network output from my desired output. And loss function helps us quantifying that difference or that distance of the current network output to the desired one, so that you can get maybe a cross entropy function. So this video is really focusing on the implementation and not exactly why we're using this loss function or why we took a certain learning rate. This is just an overall tutorial for, say, if you want to load some data, make a network, and just run training on it and then save it. And then the optimizer that will be doing these optimizations, network optimizations. So I can take this, and I have to pass all these to this func. Now we can start defining it. So it's always easier for me to start from the function signature, because then I know that this is all I'm going to get and this is what I want out of it. And now I have to decide and implement how to get to this from these. Okay. First, I can initialize the optimizer. So my optimizer is actually my optim. I want it to optimize all the parameters in my function. Again, as I mentioned, if you wanted to keep some part of the model frozen and only wanted to fine tune, for example, a particular set of layers of the model, or you wanted to have different set of learning rates for different layers of your model, then you could also do that. And then I can say max LR. You can also specify weight decay and other things here. You can go to torch.optim, and there are unbelievably useful number of parameters and optimization algorithms and learning rate schedulers that you can use. Let's leave weight decay. And then I can have a scheduler, which is again torch.optim. I've used this quite often, so I'm going to use this one. So basically what this one cycle learning rate scheduler is going to do is, you've provided the maximum learning rate. So it's going to start the trainings with a learning rate which is around 10 times smaller than this maximum learning rate. And then in about 30% of the total steps that you specify here, it's going to grow the learning rate, increase the learning rate from that 1/10 of the maximum learning rate to the maximum learning rate. And then it's going to again decrease the learning rate from that maximum learning rate to a much smaller value than what we started with in the rest 70% of the steps. These total steps are actually should be the number of epochs into how many steps do you want this learning rate to take within each epoch. And that should ideally be the number of patches you have. And the number of patches you can easily find out by doing len.traindl. Yeah. You could also specify epochs here and then steps per epochs here, and this value would have been inferred from the values provided by epochs and steps per. Now, for each epoch, in each epochs, I want to run model training. So I want to train my model. First, I want to propagate the batch of images through my model. I'll get logits out of it, basically logits. Then I want to compute a loss from these logits and labels. Now these labels are not one-hot encoded, and nor are these logits. And it is okay if you're using NN functional cross entropy as a loss function here, because it accepts labels and logits even if they're not one-hot encoded. But this may not be true for all loss functions, so you have to be careful which loss function you choose here and in what format does it want the logits, the network outputs, and labels. Once we have the loss, then we want to compute the derivative of this loss with respect to all the network parameters. So something like and then we have found the gradients, and now we want our optimizer to take a step towards the direction of gradient descent. And we've already specified learning rate, etc. when we initialize the optimizer. After that is done, we want to set or reset the gradients to 0, because we want to compute them fresh for every batch. And then, because we have a learning rate scheduler here, we should also update our learning rate by calling scheduler.step. And let me here make some in LRs. I can append so actually, if you want, you can print the state dictionary of the optimizer. So the optimizer and a model have a state dictionary, which is essentially a mapping of all the model layers to the parameter values that they hold. And in case of the optimizer, it's just a dictionary of all the learning rates or the weight decay and other parameters of the optimizer to its values. So from the parameter groups of the optimizer, I'm seeing, okay, what is the learning rate? And then I'm appending it to this because I want to keep a track of how my learning rate is progressing through these batches and the epochs. And now I can also do this exact same thing for the validation dataset. But for the validation dataset, I set model.eval so that the dropout and the batch normalization layers are not dynamic or applied anymore. And here, during the evaluation, don't need to compute the gradient or keep a track of the gradient of the loss function with respect to the network parameters. So I'll say don't update the gradients. I don't need to do any of these, but I can bridge accuracy. So loss is actually a continuously differentiable function. That's why you're able to compute this gradient with respect to the model parameters. And accuracy is a metric that you don't use for training, but for validation it's good because you can just see, okay, how many were of the network outputs were correct and how many were not. So this is a non-differentiable thing because it's a 1-0 output for every input to the network, but it's good for the validation. And these can be batch losses and batch. Sorry. Last one. This part here. And here I can find accuracy, logics, and labels. So it's something like prediction and predicted class ID, and that is going to be torch.max logics, and then these logics have this dimension batch size into n, one of the n class outputs, and I want to know the maximum in dimension 1, not 0. And then I can return the torch.sum of this predicted class ID being equal to my labels dot. So this item helps me in getting the value out of this tensor. So this is for the whole batch. So if I want the average, and here, so this thing is going to be a tensor. So I can do a torch.stack of the batch losses, and then I can do a sum or a mean over all of them. Great. And for this is already maybe just let me also return a tensor here. And do the same thing here. Great. This was for epoch. I can push it to results as average loss. Average accuracy. I can also keep a track of the train losses. And put it here, and then have epoch train loss equal to train losses dot mean train loss great. I can have all of these. Here I can return the results while also doing results LRs equal to LRs. So I think this is all correct. We initialize the optimizer, we set the scheduler, we have results, LRs, and for the number of epochs, we train the model, we get model outputs and the loss functions, update the gradients, then take the optimization step, reset the gradients, update the LR. One thing I want to do is just do it here first. So we also capture the first learning rate. Then we get the average train loss for the epoch. And then we do the model eval with torsional gradient, get the logics of the images in the validation dataset, and then this, all good. Logics. Great. I think this looks good to me. But okay, let me do it for 2 first. So our entire data is being transferred to the device, which is, in our case, it's the GPU, but the model is still on CPU. So we can do model equal to device, model device. Perfect. So now our model is getting trained. While it is getting trained, because that's going to take some time, what we can do is we can write some utilities so we can analyze the results of this training. So we know that our result is a tick like this. So I can define a plot function first of all to see what the outputs for these average validation loss and the average validation accuracy and the train function are going to be. So for that, I can say plot, and I'm going to get these results. What I want to probably do, good. I'm sorry. Maybe I can just right. Correct. I think this should be better because now this is list and I have everything in the dict, which is all corresponding to one epoch, and I think that is better. Perfect. And therefore, what I would want it to look like is that I give it this, and I tell it that I want to plot accuracies versus epochs, and then it's just computation happening at the back. Losses versus epoch. I can do a validation loss, and I want to do a average training loss both in the same graph. I want to show the learning rates versus patches. Great. And that is in LRs, I think. Right, LR. Okay. So here I get a list of pairs. So thinking for import plotlet. So I have fig and I have axis. Then of pairs, fig size equal to 10 by 10. Ah, good. So this is out. Let's see what it looks like. Great. So, okay, 74% accuracy. Great, so the accuracy had actually increased. I want to run it for, say, 10 epochs, or actually 8 epochs. And in the results, I only want to show, for result in results, print result average valid accuracy. Valid loss. This is dot item. And here also, what I want to do is I want to actually do this. Great. And I should have timed it also, and for that I could have done this, but then now it's too late. Okay, so I want to do this. I'll keep on making my plot function till then. For I make pairs. So this is the pair I'm going to get. So I will have multiple plots within this pair. And this is title and graphs or lines or graphs in pair dot items. Now axis I dot title equal to title, and axis I dot plot I'm sorry. But good, now we'll have the time for the training. And here, like I did here, I want to do this. For result in results and the multiple graphs, so I would have to plot multiple time for graph in graphs. I think this should be good. And I can also set legend here to show the graph's name. So I think this is perfect. I might have to pause the video and then resume again till the training is done. But then after that, we would also be able to quickly visualize the outcome of the training in plots. So we'll be able to see the accuracy versus the epochs, and that only makes sense for the validation dataset. And we'll be able to see the losses, both the validation dataset loss and the loss on the training dataset. And that is often useful because you often want to do early stopping when training the neural network, and you do that based on when your validation dataset loss starts increasing again, because it's very easy that you keep training on the neural network on training dataset, and if your network is especially over parameterized, you can essentially memorize the entire dataset and have your training loss keep decreasing for a very long time. But because you have now started memorizing the data, your validation loss will at some point start increasing, and therefore your test accuracy is likely to be worse if you had not started memorizing the training dataset and instead had stopped the training when your validation loss was actually low. It's usually good to visualize both the losses, the training dataset and the validation dataset losses, to make decisions on when to stop the training, etc. What we can also do is we can already prepare to save our model. So for saving a PyTorch model, what you do is you do torch.save. What you save with this is the model.stateDate. Now, as I already told you, the state dict is the mapping of the network layers or the network parameters to the actual parameter values. So this model.stateDict will contain the values of all the weights and biases of all the different layers in our network, the running mean and average for our batch normalization layers, and all the necessary parameters that are required for a model to be loaded again and used or trained on further. So we save this and then we give a path to where to save it on. So I can say CIFAR-10 ResNet x.pth. And then what I can do is I can make a new model and I can say ResNet x or ResNet x 310 torch.load. Okay, so what the save and load thing does is that save essentially serializes this state dictionary and saves it using NumPy pickle. It saves it into this file, and the load thing will then deserialize it again using pickle library and then get the state dict out of it. So you just get the state dict. You want to get the state dict from this path, right? And now you want your model to use the state dict, so you will say load state dict. Perfect. And now your model 2 should be essentially the same as this model. And how do you check that? We can run it on the test data loader and check that. So running the model on the validation dataset and running it on the test dataset should be exactly the same. The only difference is you should be able to use the outcome of the losses and the accuracies you get by running the model on the validation dataset to improve your network, but you should not get any feedback on the accuracies and losses you get by running the model on the test dataset to improve your network further. The outputs you get by validating your network on validation dataset can be used for hyperparameter tuning, decide on a better architecture for your network, and several other things. So this you can use in the feedback loop while you're training the network, but not if this was the test data loader. So I'll do an evaluate function. Put it here. And I need, of course, the model. Loss function. So you already see we, in around 9 minutes, we reached around 88% accuracy. And of course, this is just a very dummy network, and none of the parameters that I've set here, I've actually thought anything about those parameters. But what I want to do here is, I want to avoid some code duplication and also be able to evaluate the model on my test data loader. So I think this is good, and I can return the epoch average loss and the epoch average accuracy, and then I can essentially just have it evaluate model loss function. Then what I can also do is that before saving, like this, and then also here, and in this case you should see the test accuracy should be roughly random guess accuracy, which should be around 10%, and then here it should be something above 85%. So let's see. Okay. We can also plot these. Good, around 88%. I'm sorry. This is model 2. This is model 2. So you see, The model we trained on for around only 8 epochs, it already has an accuracy of around 88%. And then we create a new model here of the same architecture and of the same type, and that is necessary because otherwise you won't be able to load the state dictionary of this model into this new model. So they have to be of the same type, and we test this new untrained model that we just created on the test dataset, and its accuracy is close to random guess. And then again, when you have loaded the weights, the saved weights and biases of this model into this new model, then you get back the test accuracy of around 88%. Here's the output anyway. So this is the accuracy per epoch, and you see that you're slowly growing from here to here. And the first one I think is bad because we had already trained the model a bit, and I did not reinitialize the model parameters when I started restarted the training. And here you see the training and the validation loss. I think the first one is the validation loss, the blue one, and the orange one is the training loss, and you see that it's continuously going down, and therefore I could have actually trained the model a little more. And this is the number of learning rates, and here you see that it is indeed a bell type shape. I'll look into these graphs as to why they're not coming out as expected a bit later, and I'll also share this notebook with you. So you can see that it's indeed starting from a lower value and it's going up till the max value we specified here, and then it's again going down, and it went up for roughly 30% of the iterations or 20% of the iterations, like this, and then it goes down again. So yes, this was the first tutorial on how you define a network from scratch and load a particular dataset with all the transformations that you want to do, all the pre-processing that you want to do, visualize it as you want, define the network, and train it, then evaluate it, see some good results. I would also do a similar video of how you can do the same thing using TensorFlow, and we can see then draw parallels between how easy it is to do it in one versus the other and the benefits you get out of those two.